Hello everyone, welcome to another video tutorial. Let's continue solving the problems of the chapter 2, problem 31. Before solving this problem, let's review this section, subsection that we have here. Three-phase transformer on a common magnetic core. Yes, so as you know, we have two ways to build a three-phase transformer using three single-phase transformers or using a common magnetic core. We discussed the first one in the previous video when we solved, right, the related problem. Here we have this subsection. Let's review it. A three-phase transformer can be constructed by having three primary and three secondary windings on a common magnetic core. Consider three single-phase core type units as shown in this figure. So if we have three single-phase transformers and we connect cores, right, like this, considering this image. For simplicity, only the primary winding have shown. Okay, and also you see one slice of the core here. If balanced three-phase sinusoidal voltages are applied to the winding, the fluxes phi A, phi B, and phi C will also be sinusoidal. The flux generated by this coil, okay, IA, this is a phi A. And this is the coil B. We have this flux, phi B, and this is the coil C. Okay, so these fluxes are sinusoidal and balanced. If three legs carrying these fluxes are merged, right, this common leg, if we merge these three legs, the net flux in the merged leg is 0. Summation of three sinusoidal waveforms with 120 phase shift between them. Okay, this leg can therefore be removed as shown in this figure. Because the net flux in this leg is 0, we can remove this leg. Here you can see the reason. This is the phasor of phi A, okay, and this is the phasor of phi B. The phasor of phi C, we have 120 degrees phase shift between these three phasors. What is the summation of these three phasors? Is 0. So the net flux is 0. We can remove this common leg. Okay, this leg can therefore be removed as shown in figure 21b. This structure is not convenient to build. Okay, however, if section B is pushed in between sections A and C by removing its hooks, a common magnetic structure shown in this figure, okay, is obtained. This core structure can be built using a stacked lamination as shown in this figure. We can stack up, right, the electric steels and build this core. Both primary and secondary windings of a phase are placed on the same leg. Note that the magnetic paths of legs A and C are somewhat longer than of leg B. Yes, the flux generated by the phase B experiences a different reluctance, right, from the flux generated by the phase A. this will result in imbalance, some imbalance in magnetizing currents. However, this is not significant. So here in this figure, you can see a transformer, a power transformer. We have this core and these are windings, right? The primary and secondary windings are on, right, one leg. So yes, this is just a quick review on how we can propose this structure for three-phase transformers instead of using three single-phase transformers, and what is the reason how we proposed this design. Okay, so you can review this subsection and check. Anyway, the next section that we have is harmonics in three-phase transformer banks. So let's check. This problem is about harmonics in three-phase transformer banks. Problem 31. Three identical single-phase transformers, each of rating 20 kVA, 2300 to 230 volts, 60 Hz, are connected in YY configuration to form a three-phase transformer bank. Yes, here we have the schematic of this three-phase transformer. We connect the primary coils in star configuration and also the secondary coils in star configuration. The high voltage side is connected to a three-phase 4000 volts 60 Hz supply. Yes, this three-phase supply that we have, phase A, B, and C, and the secondary is left open. We have this three-phase load, but the side of the three-phase transformer is not connected to the load. The current of the secondary side is 0. The neutral of the primary is not connected to the neutral of the supply. The voltage between the primary neutral and the supply neutral is measured to be 1200 volts. The voltage between these 2 points, the capital N and this N. A. Describe the voltage waveform between primary neutral and the supply neutral. Neglect harmonics higher than third. Only consider the third harmonic in calculations. Determine the ratio of phase voltage of the two sides and line voltage of the two sides. C. Determine the ratio of the RMS line to line voltage to the RMS line to neutral voltage on each side. So, how we can solve this problem, and what is this voltage? Here we have this three-phase supply. The phase A, B, and C, we have balanced voltage here for the supply, and this is the neutral of the supply N. But we have a voltage, right, between these 2 points. So if we have a voltage between these 2 points, how we can calculate the voltage of the phase A, the voltage of this line with respect to the star point, and why this is important. So you remember the usage of the configurations, the YY configuration. This connection is rarely used because of problems with the exciting current and induced voltage. So remember this important point. Now let's review this section, harmonics in a three-phase transformer bank. If a transformer is operated at a higher flux density, it will require less magnetic material. Therefore, from an economic point of view, a transformer is designed to operate in the saturating region of the magnetic core. You remember HB curve of the magnetic materials we discussed in the chapter 1. Also, you remember in the chapter 1, we had a problem where we calculated dimensions of a core to have a specific value for the coil inductance. And as long as we increase the value of the flux density in the core, we can reduce the size of the core for a specific value of the inductance to have an economic design. But having a high saturation in the core makes the exciting current non-sinusoidal. You remember the sinusoidal excitation section in the chapter 1. The exciting current will contain the fundamental and all odd harmonics. However, the third harmonic is the predominant one, and for all practical purposes, harmonics higher than third can be neglected. At rated voltage, the third harmonic in the exciting current can be 5 to 10% of the fundamental. At 150% of the rated voltage, the third harmonic current can be as high as 30 to 40% of the fundamental, right? We have a high value for the third harmonic. In this section, we will study how these harmonics are generated in various connections of the three-phase transformers and ways to limit their effects. So, before going for the next subsection, let's do a simulation and check this. Here in the chapter 1, we have this sinusoidal excitation, and you remember this figure. Neglecting the hysteresis one, just consider the normal magnetization curve. Here we have this coil current, and this is the fundamental harmonic of the current. Also, we have this example in the chapter 1. We have dimensions of this magnetic, right, core, this single phase transformer. I want to do a simulation. Here we have the ANSYS Maxwell model of the problem that we created it in the chapter 1. So I'm going to calculate this curve first, and I'm going to do this simulation. We have this core, okay, and I am going to excite it with a sinusoidal voltage and measure the value of the current, right? Let's see, can we generate this waveform for the current when we have a nonlinear material or not? So how we can calculate this characteristic? We need to do a parametric analysis. We should change the value of the coil current, run a magnetostatic analysis, and measure the value of the flux linkage. So from here, you know the parameters of this model. I1 is the current of the coil 1 and I2 is 0. We calculated I1 equal to this number to have 1.2 Tesla in the core. But I am going to consider a higher value for the current to have a deep saturation. So in this case, we defined also these two groups for matrix calculation. We can measure the value of the flux linkage for the coil 1. Anyway, in optimetrics, let's add a parametric analysis and change the value of the current from negative 3 to 3 amps, the step size 0.2. Okay, the step size 0.2, here is the calculation table. We are changing the value of the I1 from negative 3 to 3 amps and running the simulations to calculate the flux linkage. So let's clear all previous solutions and analyze this parametric analysis. So after completion of these simulations, we can generate this characteristic. The flux linkage of the coil 1, the primary coil, versus its current. Okay, perfect. We can do these simulations in this powerful software. So in results, we can plot the value of the magnetic flux of the group 1 as a function of its current. Just we need to multiply this by the depth. The depth of the problem was 5 centimeter. Yes, you remember the parameters we used for this model. Okay, so generate report. Here you can see the curve. In the problem, in the chapter 1, the permeability of the core, we considered it equal to a constant number. But here in this case, I used this nonlinear magnetic material, this silicone core. You can see the BH curve of this material here. Anyway, so here is the flux linkage characteristic. Okay, we will use it to do this simulation. Now let's generate the model of this problem in the Simplorer. Yes, we are going to apply a sinusoidal voltage source to this inductor. This is the resistance of this inductor. Okay, so in Simplorer, let's add a new Simplorer design. From the basic elements, we need a voltage source, we need resistor, and one inductor. So here, let's do the connections. Yes, this is the equivalent circuit model of this magnetostatic problem. Right, in the magnetodynamic case, when we apply a sinusoidal voltage to the coil 1. Yes, so the lumped parameter model of this structure that we have. What is the value of the voltage? We are going to apply a sinusoidal voltage. The amplitude, let's consider 500. The frequency 50 hertz. Anything else is okay. And here, the value of the resistance. We should calculate the exact value of the coil resistance, but it's not important. I want to consider this number because we are going to do a qualitative analysis, not quantitative. So just to check the waveforms. Here, first, let's do a simulation considering a constant value for the inductance. So if we don't consider a nonlinear value for the inductance, a nonlinear characteristic, so we should have a pure sinusoidal waveforms for the current and the voltage here. Okay, so let's set the initial value of the inductor current equal to 0. So in this case, let's do a transient analysis. Here we have this transient solver. Here is the minimum time step, maximum 1 millisecond, and the stop time. Let's set it 500 milliseconds, zero point 0.5 second. So analyze. Yes, this is not a complex problem. You solved it in the electric circuit course. Yes, we have a sinusoidal voltage, we have a resistor, inductor here, so we should have a transient for the inductor current. If I plot L1.I, this is inductor current. Yes, we have this waveform. Here we have the steady state value, and this is the inductor voltage. So if we focus on the last time period, as you can see, here we have pure waveform for the voltage and current. The value of the current, this one, is right between these two numbers, the minimum value and maximum value. You can set the range. If I set the maximum value equal to 2, this is better, right? So, yes, we have a sinusoidal current, a sinusoidal voltage. But what if we apply a sinusoidal voltage, but we have a nonlinear inductor here? So in this case, because the characteristic is nonlinear, is like this, we have all odd harmonics, right? So let's check again, like before, we need to set this characteristic I, right, as a function of the flux linkage. We calculated this characteristic here in the ANSYS Maxwell, but this is flux linkage versus I. Let's export it to desktop in the tab format, my data.tab. Okay, when the value of the current is 3 amps, the value of the flux linkage is close to 1.5 Weber. Here is the data. How we can rearrange this data. Here the first column is current, the second one is flux linkage. So let me cut this in MATLAB data. We can define this matrix. So plot data, the first column, data 1 and data 2. Okay, so yes, the first column and the second one. So the x-axis is current, the y is the flux linkage. But here in the simpler, we need to set the the current versus the flux linkage. We need to have this graph. This is the flux linkage and this is the current. We can reverse the order, not too complex. In MATLAB, if I plot this 1, 2, So you can see this graph. Okay, here we have this actually, you know, we should smooth this graph and import it into simple order. If we don't smooth this graph, we have some numerical calculations, not important again for this analysis. So consider this important point. So here, let's consider this new matrix. Just I reordered the columns, the second column first and the first column second to reverse the order. Now I can copy this here, paste my data. This is X and this is Y. Let's save the notepad. Here in the simple order, let's define the dataset, 1D dataset, import my data. So this is the characteristic. Okay, done. Okay, yes. So we have set the nonlinear characteristic here. Now, again, if I analyze this problem, you can check. Yes, in this case, again, we have this transient. The inrush current is very high. Okay, the value of the voltage and the current. So let's focus on the last electric period. So here we have time. Click on this axis, the minimum 480 milliseconds, right? 1 millisecond, right? Excuse me, one electric period is 20 milliseconds. The minimum value and maximum value for the current is set. And also here you can see the waveform of the voltage. So in this case, we are applying a sinusoidal voltage, but the current is not sinusoidal. Yes, it's like this. Because of deep saturation, odd harmonics, yes, you can see this waveform for the inductor current. So this is for this single phase case. But what about the three phase? Okay, in this case, we have a right voltage source here. This is sinusoidal. And let me do another simulation. Also, this is important. What if we replace the voltage source with a current source? In this case, I want to force the current of the inductor to be sinusoidal. So the coil voltage will be non-sinusoidal. Okay, so this is important. Here, if we apply a sinusoidal voltage, we will have a sinusoidal flux and we will have a non-sinusoidal current. So we can do reverse. If we apply a sinusoidal current, we will have a non-sinusoidal flux and a non-sinusoidal voltage. So let's do that. I can copy this. Just what was the peak value of the current? Around 5. If I replace this voltage source with this current source, okay, the peak value equal to, let's consider for the frequency 50 hertz. That's all. So let's analyze the simulation and plot the waveform of the current, okay, of the inductor 2 and waveform of the voltage. Perfect, right? So here, in this case, we apply a sinusoidal current, but we have a non-sinusoidal voltage. The unit is kilowatt here, and this is just because of the calculations I said. Let me reduce the time step size, okay, for numerical calculations, and also reduce the value of the current here to 2. Run again. Now you can realize the difference, right, between the voltage source and current source. Here we are applying a sinusoidal current, but we get a non-sinusoidal voltage. Again, I say these discontinuities are because of smoothing the function that we have. This function, right? We should smooth this, and this, right, discontinuities in the derivative of this function are important for this analysis. Anyway, here the voltage waveform is not sinusoidal. So why this is important? Because in the three-phase case, when we have a star connection, we will have an important point that let's review it first here. For the right harmonics in transformer banks. Here, consider this image. Here we have a three-phase voltage source A, B, C, and this is the neutral point of the source. We have a star connection here and delta connection here. We have these two important switches, SW1 and SW2 here. So the first case, the SW1 is closed and SW2 is open. So this is closed and this is open. In this case, because SW2 is open, no current flows in the secondary winding. The currents flows in the primary or exciting currents. We assume that exciting currents contain only fundamental and third harmonic. Mathematically, we can write this. So this is the current of the phase A. Here we did this simulation. This is the voltage waveform and this is the current waveform. So we are applying a sinusoidal voltage, but we have this current waveform. And according to this equation here, just we considered the fundamental harmonic and the third harmonic in the waveform of the current IA. So in this case, here is the fundamental harmonic of the phase A. This is its third harmonic, okay, for the phase B and phase C. So here is the IB and here is the IC. What is the value of the current here in this neutral line I n prime n? The current from the start point to the end point in this case. So is the value of the current of IA, IB, and IC. We should write a KCL here. So if you write this KCL, the value of the current will be equal to 3 times amplitude of the third harmonic times the sine of omega 3 times omega t. Why? Because as you can see here, according to this graph, the fundamental harmonics, the summation of the fundamental harmonics is 0, but third harmonics, right, are in the same phase, right? Summation of third harmonic currents is not 0. So this is the current of the neutral point. Anyway, in this case, note that the fundamental fundamental currents in the windings are phase shifted by 120 from each other, whereas third harmonic currents are still in phase. They have the same phase. The neutral line carries only the third harmonic current, right, as can be seen in this figure. Because the exciting current is non-sinusoidal, the flux linkage in the core and hence the induced voltage in the windings will be sinusoidal. The secondary windings are open and therefore the value of the voltage, right, V delta 0, that is the summation of VA, VB, VC is 0. Yes, let's summarize. Here we have a balanced three-phase source. SW1 is closed. We have fundamental harmonic and third harmonic for the currents. When we close this switch and we have non-sinusoidal currents, yes, if we allow that the current to be non-sinusoidal, we have a sinusoidal flux in the core. This sinusoidal flux will induce a sinusoidal voltage. So here we don't have the third harmonic for the induced voltage, and consequently when the SW2 is open, how much is the voltage? V delta 0 is summation of VA, VB, VC, that is 0. So we don't see the effect of the third harmonic, right, in the voltage, induced voltage for this delta connection. So, but what if we, right, open the SW1? So in the case that SW1 is open, the third harmonic current cannot flow, right, in this line. So the coil current will be sinusoidal. And you know, when we force that the coil current is sinusoidal, its coil voltage, its flux linkage will be non-sinusoidal. And in that case, because we have a non-sinusoidal flux in the core, the third harmonic of the flux in the core will induce third harmonic voltage to the secondary coil. So in this case, the third harmonic currents cannot flow in the primary windings. Therefore, the primary currents are essentially sinusoidal. Yes, the third harmonics are in the same phase, and because we open this switch, we actually force that the third harmonic of the current to be 0 for primary coils. In this case, if the exciting current is sinusoidal, the flux in the core is non-sinusoidal because of nonlinear characteristic of the magnetic core. We checked it for this simple example, okay? And it contains third harmonic components. This will induce third harmonic voltage in the winding. The phase voltages are therefore non-sinusoidal, containing fundamental and third harmonic voltage. Okay, so here VA, the voltage of the secondary coil of the transformer A, is VA1 fundamental plus the third harmonic. Yes. And here, if you sum up all terms, the value of the voltage V delta 0 is 3 times the value of the third harmonic voltage, because the third harmonics are in the same phase. So in this case, when the SW1 is open, we have third harmonic, right, for the induced voltage for these coils. with delta 0 is 3 times the value of the induced voltage for the third harmonic in one coil. So the next case, when SW1 is open and SW2 is closed. So if we close SW2, the third harmonic voltage will drive a third harmonic current around the secondary. This will provide the missing third harmonic component of the primary exciting current, and consequently the flux and induced voltage will be essentially sinusoidal, as shown in figure 24C. This figure. This is the current in the secondary side, IS delta. So let's summarize these three cases. The first one, yes, we have these Y connections here. We have a delta connection. This is open. The switch, we have this delta. This is open and this is closed. So in the first case, if we connect the star point to the neutral of the supply, third harmonics are available for phases and this voltage is 0. Summation of VA, VB, VC. If we don't connect, right, the star point to the N of the supply, we have a voltage here. This is 3 times VA3, the third harmonic. In this case, the current is 3 times I3, the third harmonic. In this case, again, we don't connect the star point to the N and we connect this switch. This switch is closed. We have third harmonic current in the delta. So this is actually corresponding to this one. And we will have a sinusoidal flux in this case, a sinusoidal flux, in this case, a non-sinusoidal flux, and in this case, sinusoidal. So this is the case that we have Y delta connection, but what if we have Y connection? So in this case, we don't have this path for the third harmonic of the current. In this case, we can use this option. For high voltage on both sides, it may be desirable to connect both primary and secondary windings in Y case configuration. As shown in the figure 25, in this case, the third harmonic currents cannot flow either in the primary or in the secondary. A third set of winding called the third winding connected in the delta normally is fitted on the core so that the required third harmonic components of the exciting current can be supplied. So this is the case. If we have to use this transformer Y configuration, we can have 3 sets of coils. So connect the load here to this set of winding, and also we can have another delta winding, right, for the third harmonic, right, to have this third harmonic current in it. Let's see this in the simpler. Let's see this in the simpler. I want to copy this model, paste it here. So let's delete this one, and suppose we have a 3-phase source, star connected, this three-phase source, and here we have, suppose we have these three inductors. So let me, okay, copy this. This is also a star. Okay, so let's rotate this one and this one. A star connection. So the value of the phase is negative 120. The value of the phase for this voltage 120. Let's perform this connection. Okay. Connect this to this phase and this to this one. That's all. Consider the correct polarities. Positive, 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 negatives. This is the N point, the neutral point of the supply. And this is the star point. So let's run the simulation and check the waveforms of the voltage and current. So in this case, let's measure the value of the voltage. Measurement, I want to measure the value of the voltage of the right this point with respect to this one. So this is sinusoidal, Vm1. This point with respect to the right star point, this is non-sinusoidal. Yes. And also let's copy and paste this. Calculate the voltage of the star point with respect to the neutral point of the supply. Run the analysis. In this case, we don't have any connection between the right point N here of inductors and the supply for the primary. And what is the waveform? This is the waveform of the voltage and waveform of the current, because here we considered higher harmonics. Also we have harmonic 5, 7 and so on. But if we only consider third harmonic, this current will be sinusoidal, not important. So let's plot the value of the Vm1, Vm2 and Vm3. Let's have them on the same graph. Vm2 at trace Vm3. And let's focus on the last electric period, 480. Yes. So here you can see this is the source. This is the right voltage of the endpoint of the load with respect to the endpoint of the supply. Its frequency is 3 times the fundamental frequency. And this is the voltage, right, of this branch. You know that when we have a function like this is f, that is equal to f1 sine of omega t plus f2 sine of 3 omega t and so on, right? This summation, when we have these harmonics, what is the RMS value of the f? The RMS value of the f to the power 2 is summation of RMS values for these functions, the Parseval identity that we have. So, okay, here is the important right point of this problem. But what if we connect this point to the this point. The end point of the right this connection to the neutral of the supply and rerun the analysis. In this case, we allow third harmonic to flow through this line, and the value of the third harmonic voltage is 0. This is Vm1, Vm2. We have sinusoidal, right? Flux, sinusoidal voltage for this inductor. So perfect. You can do this type of analysis in the simpler. So what about our case? What about our case? We have the voltage of the A line with respect to N. The supply line to line voltage is 4000 volts. So A with respect to N is 4000 divided by the SQRT of 3. That is equal to this one. What is the voltage of the N with respect to the capital N is given here. This is the voltage due to the third harmonic. Yes. If I delete this one, don't connect this point to this point, and this one. This is the RMS value of the third harmonic voltage. So is given here. What is the value of the voltage here? VAN. This voltage, we can use the Parseval identity. That is equal to this one. VAN is VAN plus VNN to the power 2. We have this, right? The voltage between the primary neutral and the supply neutral is measured this voltage. So we have a higher voltage here. Also, you can see this in this figure. If I calculate the RMS value of these three functions for the last electric period, the RMS value for the last electric period is this one. So this is the source. This is the voltage of this branch, and this is the voltage of the neutral with respect to this point. In the simpler, we are considering all harmonics, but let's check. 353.5, 353.5, the voltage of the supply. What is the voltage of this? The neutral point of the load with respect to the source, 153.7 plus 153.7 to the power 2 calculate the SQRT. 385. 385. The RMS value of this voltage. Perfect, right? So the effect of the third harmonic is important, and you can now realize that why the S star S star connection has this problem. And when we actually design the transformer, the core, and we have a deep saturation in it, we should care the third harmonic. So finally, we can calculate the ratio of the line-to-line voltage. The line-to-line voltage is 4000 volts. The line to neutral point voltage is this one we calculated. The ratio is 1.52. In the case of a pure sinusoidal, a balanced three-phase system, you know that the voltage of the line is SQRT of 3 times the voltage of the phase. This is 1.71 But in this case that we considered the third harmonic, this ratio is lower than 1.71 square root of the 3. So this is the point of this problem. And here you can see the right equivalent model. We have these two induced EMFs, the fundamental harmonic, the third harmonic, because in this case the right third harmonic cannot flow through these coils. We have this non-sinusoidal flux, the third harmonic, and consequently, yes, we have this equation to calculate the RMS value of the A with respect to N. Okay, so now let's solve the part B. Just before solving this part, I modified the direction of this vector here and this vector. This is the correct one, and we used this Parseval equation to calculate this voltage. Anyway, determine the ratio of phase voltage of two sides, the primary and secondary. So here is the case. We have these two induced voltages for the primary. Yes, the first harmonic, the fundamental one, and the third one. So let's write here, this is the voltage of the primary for fundamental harmonic. This is voltage of the primary for the third harmonic. Okay, also we have four other phases, right? This one and, okay, the fundamental and third harmonic. For the secondary side, we have the same, as you know, just this is V2, the secondary side. And we can use superposition. You know that for this harmonic, if we have this turns ratio for the single phase transformer N1 divided by N2, what is the value? The value is equal to 10, okay? 2300 divided by 230, which is 10. So here V2 for the fundamental harmonic, the ratio we have is V1 for the fundamental harmonic divided by A. And for the third harmonic, again, we have this equation. So you can again use the Parseval equation. We have A in this square root. We can factor it. And again, if you compare the RMS value of the voltage for the secondary phase divided by the primary is the same, is A, 10 again. What about the line to line? The ratio of line to line voltage, the RMS values, is again equal to 10. So you can investigate that for this star star connection. Okay, so if you check the figure, I think 25, we have, right, these four combinations. Okay, so in this case, the ratio of the line to line voltage, right, is the same as the single phase transformer. But in the Y delta connection, if you check the ratio of the line to line voltage, right, for this case and this case, we have this number also, square root of 3. You know that. So this is the right solution of the part B. How you can calculate this in the simpler software? Here you can use 3 transformers and run the simulation again and measure the RMS values for the output and check. So here in the Simplorer, we have this single phase transformer with nonlinear material. Okay, this is a single phase transformer with a linear magnetic material. The parameters: main inductance, leakage inductance, the winding, yes, resistance, primary side, the parameters of the equivalence circuit. And here we have these parameters for the nonlinear transformer, single phase transformer. Again, we have losses. Okay, here we have leakage inductance for the primary and secondary, the main inductance, the main inductance or mutual inductance between the primary and the secondary. So is not in the scope of this video, right? Maybe you can investigate that in future courses when your focus is on design of three-phase transformers. Yes, so in this course, we focus on single phase transformers and just we had this topic, this short topic on three phase transformers. But you can use these elements and continue, right? This simulation, this modeling. Anyway, I think the time of this video is high, so let's pause here and continue solving the next problems in the next video. Thanks for watching.